This
So,
meeting is being recorded.
welcome everyone to the Winds and Currents webinar. Today we have Greg Jacobs from the Naval Research Lab who's going to talk about bounds of present ocean prediction. And I'll let you take it away, Greg.
Thank you, Sarah. Hello, everyone. Great to be here. This little animation that we're looking at is mixed layer depth from a numerical model as the color, but the little trajectories that are shown are GPS tracked drifters that were deployed. And that was about 50 GPS drifters initially deployed, which conceptually seems like a large number, but when you look at it in the context of the scales of features and just the number of features that are in this area, it is really, really sparse. So we've been looking at what our skill in ocean prediction is as a function of the observation resolution and what's keeping us back from advancing that prediction skill. There's a lot of different things. We could look at our understanding of physics is certainly one, and our understanding of physics colors how we set up numerical models. We set up models to represent the physics we understand, not necessarily the physics we don't understand. So they're self-fulfilling prophecies. But really, what I want to make a point of here is that it's very much controlled by the observation resolution that we have, and also connecting to Odyssey, the velocity assimilation and what impact it has. So what matters in terms of small scale features in the ocean? And this is just an example from a paper by Liu. They were looking at the Deepwater Horizon event, and they did several 2-day forecasts. They took a satellite image of the oil distribution on the ocean surface. They put that into 4 different numerical model systems, which are the first 4 columns. They made a 2-day forecast and they compared it to the verifying observations from satellite on that subsequent 2 days. So you can see each of these, the pink areas are where the particles they put in the surface of the model swept out. And there's a lot of differences between the different numerical models in what they produce. None of them did a very good job. They all did relatively poorly. Every now and then one of them would get lucky and do a reasonable prediction, but there was a lot of discrepancy and dissatisfaction. So these model forecasts were being used during the Deepwater Horizon event because the commander in charge of the whole cleanup had to determine where to position crews along the coastlines, where to position ships to skim oil. And that was a hard problem given that the forecasts were not terribly good. A big part of that was the small scale features that were occurring during that time, creating the discrepancies in the models. So following the Deepwater Horizon, there was a lot of intensive looking and understanding at the dispersion of material in the Gulf of Mexico. So this is an animation of just over 1,000 surface GPS drifters that were deployed around the Deepwater Horizon site. The tails on these are about 24 hours, and the background image is the surface currents and surface temperature from a 1 kilometer resolution model. And you can see the general structure of the flow corresponds reasonably well to the observations. But if you look at the smaller features, like this cyclone that the drifter has been trained to on the north side of the loop current eddy, there's a cyclone in the model, and you can see those 2 features move apart. Every now and then you see the cyclone in the model get pushed towards where those drifters are observing that. And then you'll see them move apart further. And after a while, that cyclone gets pushed back to where the drifters are observing that in the real world. We can go back and look at the satellite data, and what's happening there is every 2 weeks, there would be a few passes of the satellite altimeters over that small feature. They would see it and they would make a correction to the model. But the data is relatively sparse, so we end up with a model forecast that's reasonable at the larger scales, but the smaller scales, the features are out of place. It's a good model representation of the dynamics, but we can't constrain the position of where those small scale features are. So we wanted to try to quantify that a little more. We built a little framework You can look at this as a theory of what we've put together as to what's occurring. So we broke this apart as a function of wavelength. And we know the numerical model itself represents only certain scales given the resolution of the model. There's been a lot of work looking at finite difference formulas, what size features they represent, the differential equations. And typically it's on the order of 5 to 10 grid points per wavelength to represent either a first derivative or nonlinear advective terms. So this red area basically shows the scales that are controlled by the model. If we, for a 1 kilometer model here, things smaller than 10 kilometers, we just don't represent the physics. But on the opposite end, the features that we have sufficient observation resolution for, those can position the features in the model, and we have skill in larger scales, which leaves this band in the middle where we call that the unrepresented features. If you go back 20 years or so and looked at global ocean models that were a quarter degree to a tenth of a degree, basically this yellow band didn't exist. The model resolution, basically the red band extended all the way up to the green. So as computer power has grown, this red band has been moving to the right, and this big yellow band has been opening up. So we wanted to try to estimate what this scale is from those 1,000 drifters. Ideally, we would like to try to take the power spectral density of the errors relative to the observations, and we want to know where the power spectral density of the errors is larger or smaller than the power spectral density of the features that are in the ocean. We can't do that with that drifter data set. It's continually moving, it's not uniform, so we went for a little different approach here at first. Basically, if those unconstrained features in the model are out of position, if we remove those small scales from the model, we should see the errors to the observations go down. Also, since we're talking about scales of features and we're assimilating data, these drifters are not assimilated. There's a question that comes in about how the horizontal scale of the assimilation process affects the results. So we ran 5 different experiments with different assimilation scales over the 3 months of that drifter deployment. Experiment C here had the lowest errors, so we're just going to pay attention to that green curve. If you just take the model surface currents and compute the velocity difference relative to the observed drifters, take the RMS of that, you get somewhere between 28 to 29 kilometers per day of error. If you filter that, we're using just a Gaussian filter here, and remove just the smallest scale features from the model, the errors start to go down because we're taking out features from the model that are in the incorrect position. As we start to increase that scale of the filter, we're removing more and more of those small scale features until we get to a minimum. If we start increasing the scale further, we're starting to remove features from the model that we actually have skill in, and so the errors start to go up. So this filtering process is how we're getting that estimate of the scale. Here, this horizontal axis is the quarter power point of the Gaussian filter, which is about 3.7 times the E-folding scale. So for this, it's about a 59 kilometer E-folding scale where we get to the minimum. Now, the interesting thing here is, if you look at that total error, we reduced the RMS error from about 29 down to 25 kilometers per day. It's about a 20% reduction in the RMS error. What does that imply in terms of the total variance of errors these different pieces are contributing? So we reduced the RMS error to 80%, but if we look at it in terms of variance, we've reduced it to 64% of the original error. So 36% of the error variance was originally in the model unconstrained field. I'm going to assume that the variance in the true ocean is a similar quantity, which it's not. This is only a model. It doesn't represent all the variance of the ocean. So the true unconstrained variance is probably larger. But the interesting thing then is the contribution to the total error made by the constrained field is, that is the large field we have sufficient observations for, is 28%. The errors in the part of the prediction that we have sufficient observations to constrain are smaller than the contributions to the small scale features that we can't resolve at the moment. So going back to our little conceptual picture here, most of the uncertainty in the forecasts is in this yellow band. It's not in errors in what we have resolution in the observing systems now for. Now, this result depends on the relative energy between small scales and large scales, and we looked at surface velocity in particular here. There's 4 different lines here that are the average power spectral density of different variables. Surface kinetic energy is the surface velocity. 100-meter temperature is similar, so we'd expect similar results for that. Sea surface height has a much steeper slope, so there's going to be much less energy in the small scales for sea surface height, so you may get a different number. Mixed layer depth from that animation on the first slide has a much shallower slope, so there's much more energy in the unconstrained scales there. If you want a hard problem, try to predict mixed layer depth. That is hard. But the interesting conclusion is where the uncertainty is. And given the observations, we can improve the models, we can improve the assimilation, we might move that boundary between the yellow and the green areas a bit, but realistically, it's the observation resolutions that's defining where that boundary is. The only way to get around that is to increase the observation density. So here's an example of that. This was a deployment of drifters from DARPA, from the Ocean of Things project. Really interesting proposition they had of looking at quantity over quality, making small, cheap drifters with lots of different sensors that were not precisely calibrated versus making one large expensive instrument. So they deployed 377 drifters in the Gulf of Mexico. We set up 2 model experiments. Both those model experiments are assimilating all the regular data. By that, I mean all the satellite, sea surface height, sea surface temperature, all the in situ regular data. And one of those experiments was assimilating the velocity inferred from those drifters. You see those 2 colored lines in the picture on the top right? Those are 2 gliders that were out during the same time. And we kept those out from the assimilation as reserve them for as independent data for evaluating the effects of the velocity assimilation. So here's a little animation just to give you an idea of what that drifter deployment looked like. The top row is the model that did not assimilate the drifters, and the bottom row is the one that did. The left column is the surface temperature and currents, and the right column is the 100-meter temperature and currents. And the interesting feature is this warm anticyclonic eddy. And you see the drifters are in a position that's very different from that anticyclonic eddy without assimilating the drifter data. When assimilating the drifter data, they maintain the position much better. There was also an interesting event. Hurricane Sally went through the area while those surface drifters were out. We made a lot of assumptions when we assimilated that data, and one was that they are observing geostrophic currents, which when a hurricane goes by, they are certainly not observing geostrophic currents. But the system was able to get past that without a significant disruption. So just a real quick look at a few snapshots. Both those models started from the same initial condition on August 15th, and here we are on August 28th, 2 weeks later, right at the beginning of the deployment of those drifters. So the model states look very similar at that time. 5 days later, those drifters are entrained around that anticyclone, and you can already see the differences in the currents at 100 meters. There's an enclosed circulation south, another anticyclonic circulation that's already being changed by the drifters to the north. And by the time we get to September 10th, you can see on the top, the position of the observed anticyclone is very different from what's in the model, whereas the assimilative version using the surface currents is keeping that anticyclone much more in the correct position. So the size of this feature is on the order of 100 kilometers. That's smaller than we typically would expect from the previous results to be able to constrain well. So this is an example that those locally dense observations change the scales that we're able to predict. One way to look at that is just the forecast trajectory error. So every day we could put particles in the model at the observed drifter positions, forecast their trajectories for 5 days for every day of the experiment. And on average, the blue line is the trajectory error without velocity data assimilation. And the red line is the trajectory error with velocity data assimilation. Great. At 5 days, we've reduced the trajectory error by 25 kilometers RMS. You'll also notice at 1 day, the trajectory errors are about 29 kilometers. So 29 kilometers per day is about the same number we saw from all the laser drifters that were deployed in the Gulf of Mexico during that 1,000 drifter experiment. Another way to look at this is the improvement in the forecast time. You see that the error level at a little less than 3.5 days without the velocity data assimilation is the same error level at 5 days. So we've actually improved the forecast. We've gained 40 hours of forecast skill, which is huge. In meteorology, a thumb rule is that you can get 1 day of improvement of skill for every 10 years of research. So gaining 40 hours of skill is more than a decade of research if this were meteorology, but that's a rule of thumb. Now, the interesting part here is, okay, the surface velocity looks like the drifters. No surprise, we forced the model to look like that. But when we go back and look at the glider data, we look at the errors to temperature, and these are the RMS, the bias, and the mean of the absolute value of the difference. Let's look at just the RMS. And first look at the 0 to 24-hour forecast. The blue line is without data assimilation, and the red line is with data assimilation of the velocities. And you can see there's a pretty significant reduction in the RMS errors of temperature here at 300 meters depth. The black line is the standard deviation of those observations from the gliders. So this is a pretty big reduction in the RMS errors. And even in the 24 to 48-hour forecast, we're seeing a really good reduction. If you look at the surface, the errors at the surface don't change a whole lot. And the reason is there's a lot of satellite SST. You're not going to change the errors at the surface in temperature because there's so much satellite data. But we're taking surface drifters, and their big impact is in the range of 200 to 400 meters in the water column, because that's the thermocline depth in the Gulf of Mexico. We're changing the positions of eddies, so we're changing the temperature structure at 200 to 400 meters depth through that assimilation of the surface velocities. Great. Another quick example, since December 12th is coming up and SWAT is due to launch, here's a little observation system simulation experiment of SWAT. We set up a 1 kilometer nature run, sampled it with the SWAT simulator, and here we're including only the Karen instrument noise. There's some other systematic noise sources we did not include. Those were assimilated into a similar numerical model, so this is a fraternal twin experiment. And if we look at the mean of the absolute error at 100-meter temperature, that's the black line. So, yep, the errors drop down pretty rapidly, but there's this interesting oscillation that starts to occur. If you look at the number of observations that are going into each assimilation cycle every day, you see that there's an increase during which the observations go down, and then the number of observations drop, in which case the errors go up. If you take the power spectral density of that black line, there's a peak right at about 10.7 days. Why is that? Well, the SWAT orbit character is such that it lays down a series of successive swaths moving toward the west on ascending passes, and then it repeats that on descending passes. And that occurs at half the repeat period of the satellite orbit, which is 21 days. So we're seeing the effect of the observation density increasing and decreasing, having an effect on the oscillating accuracy of the ocean prediction. In this case, we can actually compute the power spectral density of the nature run and the assimilative run, and take that ratio of the power spectral density of the errors to the power spectral density of the nature run. And by definition, we said if that ratio is less than 1, that's where we have skill. Those are the constrained scales. If it's greater than 1, that's unconstrained. But we did that separately during the times. We just picked the times to compare at the minima of the errors and at the maxima of the errors. So when the errors are at the minima, we have scales of about 68 kilometers separating constrained and unconstrained. And when they're at the maxima, we have scales about 92 kilometers between constrained and unconstrained. So as the data is coming in and the satellites covering the area, we see that the errors, the scales in which we have skill go down. And as we have that little bit of a gap, the errors, the scales in which we have skill start to increase again. So another little demonstration that that observation resolution is controlling the scales at which we have skill. Okay. As that observation resolution changes, we have to adapt how we're using that data. You know, the examples before, we were taking that data and pouring it into the data assimilation approach that we use at present. But as we go to higher resolution data, that data assimilation approach really doesn't do exactly what we need. So it's starting to become a limit as well. So we're going to look at here real quick at the S-Mode pilot campaign from last October. The first operational deployment just finished up this. So this was a year ago. What we're going to look at are 9 ocean gliders that were deployed during that experiment. And the plot on the left, there's just a little plus sign at the glider location near 0 GMT every day for every glider. So there was a control system, an automated control system that was set up to control those. The objective was to maintain a distribution in that area and work toward targeting the gliders towards areas where the model forecast areas were high. So they maintained a good distribution over the area. On the top here are the profiles that were returned from one of the gliders. And they've been converted into distance. So these gliders didn't go back and forth on nice predefined lines. They were continually chasing the model forecast error that was changing every day. But we just unwind those paths and we look at them as a function of distance. We can interpolate those observations to the model depth levels and then interpolate in distance to get 1 kilometer samplings along each of those paths. Now we've got a nice uniform data set that we can compare directly to the model, and we can take power spectra density of these to look at the constrained scales. But before we do that, a little diversion into some data assimilation esoterica. The data assimilation is very much a filtering operation. Why is that? If you parse through the little equation for a 3D var or a 4D var, basically the correction the data assimilation is computing, it's a linear combination of covariance functions. So the character of the correction to the model is going to look like the character of these covariance functions. For the horizontal scale that we use a second order autoregressive function. And this is just a comparison of what a SOAR function looks like to a Gaussian if they both have a scale of 1. And this is the power spectral density of these. So a SOAR quarter power point is about 11 times what its scale is. Keep that number in mind. Just remember, this one goes to 11. So let's go back to the S-Mode experiment. On the left here, that shows the glider distribution, and it shows the horizontal length scale that's used in the standard data assimilation. It's a function of Rossby radius. There's a factor that scales it. From the early experiments, we went through a range of those different scalings and found the minimum one that's giving us the best forecast skill. So it varies spatially, but we have much higher resolution in that area of the glider observations. So basically, we took a large hammer, we put a big dent into that horizontal scale. We looked at the spacing between the gliders on a daily basis. There's several different ways you can define that. On average, the spacing was about 50 kilometers, which means they resolve about 100-kilometer wavelengths, which means given that the SOAR function has a factor of 11 quarter power point, means that we set the scale at the center here to 9. So 9 turns into 99 kilometers. So the scale in the center of the glider distribution is consistent with the resolution that they were able to observe. Great. So we ran those two experiments side by side, one using the standard scale for assimilation, one using that scale that's reduced in the location of the glider data. They started from the same initial condition, and we ran them up till September 9th using all the same data. So these plots show the 100-meter temperature from the two experiments. They look very, very much the same, which they should. They also show the data that was assimilated. So these magenta dots are glider profiles, and these white dots are Argo profiles that got assimilated that day. On September 10th is the day we switched this second experiment to use the shorter scale in the vicinity of the gliders. So suddenly you see a lot more glider data getting in. The reason is the data is thinned out, or super observations are created where there's very dense data, dense relative to this decorrelation scale. If you think of sea surface temperature from satellite, the sea surface temperature data from the satellite is much more dense than this decorrelation scale. If you put all that data in, sure, you can make a solution, but realistically, it's reducing the conditioning of the matrices you have to invert. It's costing you computer time. So you end up throwing a lot of it away. Because the scales are larger in this experiment on the left, you can see on September 10th, there were maybe 5 glider profiles included. And on September 10th, with the reduced scale, it's including a lot more data because it thinks the scales are smaller. When you look at the increments at 100 meters depth, you see that the corrections to the model on that day are smaller scale in the adaptive assimilation than the regular assimilation. Great. It's doing exactly what we would want it to do at this point. And here's the evaluation. So again, we can compute, given that we have depth versus distance of both the glider data and the model, the power spectral density of those, and we can look at the ratio of the power spectral density of errors to the power spectral density of the variability itself. So on the bottom right is the power spectral density of each of those depth distance data sets. So from 9 gliders, there's 9 data sets averaged together here. And one thing you have to be careful of, these are not power spectral density that you might think of as the ocean, because these are meandering little lines. So they're not along a nice straight line. So don't take this as the scales or the variability at scales in the ocean. But on the plots on the left, the top one is from the regular experiment using the regular decorrelation scale. And this dark contour, the black contour line is where the error is equal to the variability of the ocean. So areas where the errors are less, that's where we have skill. Areas where the errors are higher, that's where we don't have skill. And just coincidentally, that turns out to be about 220 kilometers. When we use that adaptive scale, the scales at which we have skill go down to about 80 kilometers, not too different from the 100-kilometer quarter power point we chose. And the depths at which that reduction is occurring is mainly around the high variability at the thermocline depth that was observed by the gliders. So again, we're using the data a little more intelligently, making corrections where the data resolution says that we're able to, and we're making corrections in the mesoscale eddy field. Getting the mixed layer depth here at 40 meters is still hard. While we get some improvement in the scales we're predicting there, it's not great. There's just a lot of variability in mixed layer depth that keeps it a hard, challenging problem. So, okay, so here's where we are. We've gotten to the point where computers have advanced. We can run models at very high resolutions on a regular basis that represent physics at scales smaller than we can observe. We found from the evolution of the surface velocity from the drifters, the majority of errors is in this unconstrained band in the yellow right now. We see through the Aussies that SWAT is going to move predictive skill to smaller scales. So higher density data is moving us to the higher skills at smaller scales. We can take that surface velocity information and use it to correct the deeper ocean temperature and salinity structure. And realistically, the reason is those drifters act as little altimeters. If you assume the flow is geostrophic, they're basically telling you what the gradient of sea surface height is and in what direction that gradient is. But since they're drifters, they're entrained in that area and they're persistent, which is really great. and adapting the scales that we're correcting to be consistent with the observation resolution pushes our skill down to smaller scales as well. So that's the last slide. Thank you.
Thanks, Greg. This is great. Questions for Greg? And maybe while people are thinking of questions, I'll start by asking about, you've really focused on spatial scales, and I'm wondering about time scales and what time scales matter for observations in your studies.
So if you imagine one perfect snapshot at infinite resolution, the time period between successive snapshots is going to limit what the skill is as well. For larger scales that have a long time period, we've shown, yes, we have skill forecasting larger scales out at months. So right now, we've implemented a global ensemble system that's a coupled ocean atmosphere ice system. It runs a 45-day forecast every week. And in the ocean, for predicting large-scale eddies, it has skill out at 45 days. So the hard part are the smaller scales. Mesoscale features, they propagate somewhat under their own dynamics. They certainly influence one another. They merge and push each other around. But submesoscale eddies are more like tropical cyclones that are steered by the larger atmospheric circulation. So submesoscale eddies are steered by the mesoscale currents. So if you have a small error in the mesoscale currents, that's going to lead to a rapidly growing error in the submesoscale field. So we've looked at in the Aussies, the wave number frequency spectra, and yeah, at smaller scales, the frequencies at which you have skill become longer. You only have skill at large scales at large spatial scales at short time scales. You have a really hard time getting both short spatial and short time scale skill. That was the long answer.
Thanks. Other questions for Greg? Yeah, Melanie has her hand up.
Hi, thanks for a really interesting talk. As the observations of surface currents within a few kilometers of the coast become available from, for example, a new satellite mission, then those data will be in the region where, I'm sure you know, the currents become very anisotropic and polarized parallel to the coast and the isobaths. So how much would the assimilation machinery need to be changed, and is it possible so that you're not assuming that those, the covariance functions or the balance operator is horizontally symmetric?
Right. It would have to change a lot. So what we've been looking at here are mainly deep ocean features.
Mm-hmm.
They're primarily geostrophically controlled. And like you said, when you get into the coast, there are a lot of other sources of error. When we look at mesoscale eddies, what's the biggest source of error in a forecast? It's getting the initial position of the eddies right. In the coastal areas, a large part of the error is from wind forcing. So if we saw an error in sea surface height or velocities in a coastal area in shallow water, mm-hmm. we would not change the temperature structure to try to match that sea surface height.
Yeah,
that would be do some interesting things that would be very bad. But it is possible to take those observations and track them back through four-dimensional variational approaches that consider the dynamics of the system, mm-hmm. and actually propagate the observations back to things like the wind forcing or other sources of errors. So it's very possible.
And would you have to do that by separating the velocity into a long shelf and cross shelf component and assuming different dynamics for those two components?
You should, definitely.
Yeah.
We know they're different, and it's going to depend on the particular situation, and it can change from day to day. So a lot of people look to those advanced data assimilation methods that can take those factors into account.
Mm-hmm.
It's a really challenging problem. Some people have done some really great work on it, though.
Thanks.
Next, I think Tony has his hand up.
Hi, Greg. Thank you very much for the very interesting presentation as well as the successful experiments. Very encouraging. So I have a question. As you said that the error covariance is right at the heart of the data assimilation. So I have two questions. One is, what is the best strategy to constrain the data assimilation so that it can improve the representation of the interaction between, say, small mesoscale and large mesoscale, or between some mesoscale and mesoscale interaction, given that the shape of the the correlation scale or error covariance are prescribed? So that's question number one. I'll ask number two later.
Okay. I think a lot of people have been looking at multi-scale approaches. So it's basically making successive corrections. And in the first pass, you would make corrections to the mesoscale field, and the second pass to the submesoscale. And that, in each of those, you would change the horizontal length scale, of course, but also you would change what you would assume to be the vertical structure, the relation between temperature, salinity to the surface. So those are approaches that people have been looking at quite a bit for addressing that kind of problem.
Okay, thank you very much. And then the related question is, the error covariance, are the relations between surface current and surface temperature and salinity and the subsurface variable used in deriving the error covariance for the assimilation?
Oh, yes. So for a lot of the experiments we looked at here, they're using a three-dimensional variational approach. And yes, we have to specify what that expected error relation is between temperature, salinity, velocity, all of those. So typically, we assume that the structure of the errors are similar to the structure of the features. So we assume that the vertical covariances of temperature and salinity are similar to the vertical covariances of what's been observed in the past. So we take all the historical observations, build those covariances between temperature and salinity at all the different depths, and we assume that the errors are similar to that. So it kind of bakes in climatology in a way, and it makes everything in some ways look very climatological, which has some benefits, but also a lot of drawbacks if you have anything that doesn't look like climatology.
Yeah. Thank you very much, Greg.
Thanks. Next is Fabrice.
Yes, very nice talk. Very happy to see this nice developments. I had two questions. One is going back on the question of time versus space. I was wondering if you have any plan before the Odyssey proposes due next June to maybe repeat some of these analysis of these twin fraternal twin kind of experiment with simulated Odyssey data to kind of show the benefits in terms of time of having something as frequent as Odyssey compared to an altimeter like SWOT. That's the first question. And the second question is, we've had a lot of scratching our heads for SCIM on the issue of near-Earth oscillations. And if I understand correctly, at least where you are now, you really need to go to this geostrophic approximation to be able to project the surface velocity onto the other variables. And so I guess that in many regions of the oceans, that's actually is probably okay, as you've shown that for the Gulf of Mexico. But in other places, we probably have to be able to split the data between NIOs and other things. And so I don't know what you can say about that.
So there's the part of me that says, oh yes, I really, really want to do this to do a simulation of Odyssey. And the hard part is by the deadline of the proposal, given the time constraints. So we keep trying to work that.
I guess could be a bit later, but that would be really nice to, yeah.
I know. What we did with the drifter data, okay, since we have a 15-minute sampling of the drifter data, we define velocity as velocity averaged over an inertial period. So for the drifters, we could essentially take positions separated by one inertial period, which would remove those high frequency variations from the drifter data. And when we difference them from the model, we did the same thing with the model. We averaged the model over an inertial period to remove its high frequency variations so that we wouldn't have that representation error contaminate things as much. It'd be closer to our assumption of geostrophy. For something like Odyssey, obviously that's a lot harder.
Right.
Don't have a good answer off the top of my head. Sorry, Fabrice.
Well, it's not easy, I guess.
Yeah, lots to think about. I wondered if you thought at all about HFR data. I don't know how available they are in the Gulf of Mexico.
There's a few sites running. There's a National Academies program, Understanding Gulf Ocean Systems, that's implementing a few additional HF radar sites to cover the Florida Straits and the Yucatan Strait, I believe. We've done some little experiments looking at HF radar, but not a lot in our group. So I don't have enough experience to say offhand what the impact would be.
Tony has his hand up again.
Sorry, it's a related question about HFR data simulation. So I heard that Jim Cumming, who was working in NRL before, has developed a surface current data simulation for NOAA as well, EMC, which I don't know the nature of it. Might be similar to what he developed at NRL, or is it different? The surface current simulation.
I'm not sure. I haven't seen the details, so I don't know offhand. But yeah, I know the work. We have a copy of the data simulation code that we put together agreement with NOAA so that they can use that in their operational systems. And I haven't kept up with the details of what they've been doing in the development of that. So I don't know offhand.
So the NOAA EMC said they have the capability for assimilating HFR data already. So I suppose it's the same in your group at NRL?
I don't think it's the same because the vertical projection of that velocity into the temperature and salinity structure is something newer.
Okay. Got it. Thank you.
Any other questions looming? I think I have one more, which is you mentioned as you move to higher resolution, moving from having super merged observations to actually taking all the observations. And that made me wonder, if we deal with a satellite product, a potential Odyssey product, and we have a choice of merging observations to beat down noise or using them with noise at the satellite postings, what would be the likely path for the NRL system, do you think? Do you know?
It's a hard question. The big thing to consider are the correlated errors. White noise errors are just not the problem. If it were possible to have SWAT resolution at the onboard resolution, it would be just super fantastic, because it doesn't matter what the white noise errors are. they get beaten down very, very quickly. So maintaining the resolution is probably preferable because you'll not preclude different applications of the data by the spatial averaging. If you average spatially to get the error levels down, you could preclude somebody's coastal application, for example. Letting people decide for themselves for the particular application they're working on, which is better, or what resolution averaging is better, would keep your user base open more. And that's the answer off the top of my head.
Should we go to Roger?
Oh, hi, Greg. Nice talk. I just wanted to follow up on that question about near inertial oscillations and the Gulf of Mexico drifter experiments. Is it possible for you to go back and look at what the, how the model did at predicting those near inertial oscillations and what it would have done if you had tried to assimilate the full or pieces of the drifter measurements that
Yes.
that had that signal?
Yeah, I see what you mean. Oh my gosh. Every time somebody asks, can you do that? The answer is yes, we can do anything. I think that would be a really interesting problem. We had done some evaluations from the laser experiment, the 1,000 drifters in the Gulf of Mexico, evaluating the rotary spectra of the drifters to the model. And there certainly is skill in the models in the rotary spectra. So those inertial oscillations, is it sufficient to remove them down to error levels that are necessary and for velocity observations? I don't know off the top of my head, but that's a really good question. I'm adding that to my list.
Okay, thanks, Greg.
And let's go to Fabrice.
Yeah, it's back again on this issue of noise and resolution. I guess one of the issues for altimeter assimilation is the mean dynamic topography. And could you say a little bit what kind of mean dynamic topography product you're using and how you would see a possibility for Odyssey or something like that to be able to derive a very high resolution mean dynamic topography from satellite data?
Right. So yeah, you're right. The mean dynamic topography is a quagmire of a problem, and so we've avoided it. We take the sea surface height anomaly from the altimeter, and then from all the historical in situ data, we do the covariance between the surface steric height anomaly to the temperature and salinity anomaly beneath. So everything is done in terms of deviation from the mean. And of course, after we do the analysis, we would add the mean temperature and salinity back, but that comes from all the historical in situ data. So we've never really had a mean dynamic topography that we're using in the process. It's implicit in the mean temperature and salinity that we add back.
Okay.
Great. Tony, did you have a final question?
Greg just answered my question. My question was about anomaly assimilation. So thanks.
Great.
I think that dynamic topography is a vexing issue that everybody continues to go around about. So it'll never get solved to everyone's satisfaction, but advancements that can be made on that would be great.
It will lead to questions about other sensors that might do better at high resolution than low resolution. Potential Odyssey issues as well.
Yes.
So it's good we have the machinery in place to deal with anomalies. If there are no further questions, let's wrap this up. Thank you very much, Greg. This was really wonderful. Big round of applause.
Great fun. Thanks, everyone.
Greg.
Thank you, everybody. I'm going to stop the recording.